Right, back in chapter 4, we talked about designing experiments. And one of the special cases we talked about was where we had paired data, where instead of giving two different treatments to two different people, we gave the same two different treatments to the same person. And this had the effect of reducing variance. And so that resulted in what was known as paired data. And when we do this, when we start doing hypothesis testing, we're going to start comparing in the next chapter means or proportions in two different populations. And so paired data will a lot of times when you first look at it look like you're supposed to use one of those things where it's two different populations. And so it's key to make sure that you identify when you do something on the same individual. So here's treatment A, here's treatment B, here's individual 1, individual 2, individual 3, individual 4, individual 5, individual 6. And so when we do hypothesis testing on data like this, what we're really looking at is the difference. And this is B minus A. And so while there may not have been a clear pattern in A or a clear pattern in B, a pattern will emerge in the difference, and we would use this data set for our hypothesis testing. Here we'd have to be very careful because n is less than 1, 2, 3, 4, 5, 6, 7. So n is 7, so we'd want to know that this data came from a normally distributed population, and we'd want to look at the data. But when we do, this is the big thing, is not doing the test, because it's the same as the test we did last class. It's just that instead of using the data set, we're using the difference. And we'll practice this a lot in the next class. And you would do a paired T procedure. The steps that you do are the same, it's just that instead of using, you use the difference data. You use mu D here. Once again, we'd still check all the conditions. Were the people randomly selected from the population? Did we sample less than 10%, or do the people make up? In an experiment, actually, we don't worry about sampling 10%. We just worry about, did the effects of one person influence the effects of another? And we'll talk about that more in class 2. But the conditions for independence are different in an experiment than in a sample. But it's the same T procedure we did last class. And generally, your null hypothesis is going to be that there was no change. Oops, sorry, there should be an asterisk here. Your null hypothesis is going to be that there was no change. And we'll get into this more next class. But it's the key is identifying it. The hard part's not doing the procedure. The hard part is realizing that it's paired data and not two different sets of data. Now, let's talk a little bit about the reality of hypothesis testing. And this is something that we see, and I've talked about, and we'll talk a lot more about after the AP exam, but it's still something that while we're paying attention we need to talk about, is that just because we have statistically significant evidence doesn't mean we have meaningful evidence. And statistical significance means that we are mathematically able to show that there's almost no chance something happened by random probability, that we just didn't get unlucky. It's very unlikely that we got a certain result based on the null hypothesis and the sampling distribution based on the null hypothesis. But if we have a large enough sample size, we can prove very, very small differences. But very small differences don't necessarily have any meaning. Let me talk to you about what I'm meaning. First of all, alpha level will change in different fields of study. In the medical field, they'll generally have a much smaller alpha level because side effects can have there can be large side effects from a drug. And so the type 1 error is bad. We don't want to be giving drugs with side effects that don't actually work. Um, and so we want to look at the confidence interval and and see how much change there actually was. Not just was there a change, but how much change. Let's say we um, designed a whole new curriculum for AP Stats. I flipped my classroom and I showed there's a statistically significant jump in test scores by doing a sample at like 3 schools in a local school district. But the test increase was 2 points. So the average grade went from a 78 to an 80. And I had a large enough sample size that will prove it. And so yes, it did help, but did it help enough to offset the costs, or would that money be better spent elsewhere? Would our efforts be better put in another situation? And we'll get into this in class. And so a lot of times the confidence interval will give you a lot more information of how much change there actually was. Because just saying that there was some change is not necessarily all that useful. If the original experiment is poorly designed, no amount of statistical analysis can fix it. So we always want to check on how data was collected. You'll hear all these stats on the news, and you'll hear things in the newspaper that are being reported, and unless you've seen the original paper, you should always take it with a grain of salt, because a lot of times the way the data was collected in something that's like counterintuitive or revolutionary that they're trumping about was not sound. And so while the statistics back them up, it was basic flaws in the original design render those statistics meaningless. Let's just talk about when we actually need to do significance testing. Suppose you want to know the average GPA for a student at your school who was enrolled in AP Statistics. Since this isn't a large population, you conduct a census and record the GPA for each student. Is it appropriate to construct a one sample t-interval for the population mean? And the answer is no, it is not. Because the whole reason we created confidence interval is because we took a sample and we're trying to guess the true proportion, the true parameter, I'm sorry. You know, we estimate mu with x bar. But if we have mu, we don't have to estimate it. We don't have to do any confidence intervals. And that's a common mistake, is people will be like, well, we need to do, you know, statistics. You can't just show there's an increase because, well, yeah, I can if I did it to everybody in my class. And if it's a census, a change is a change. The other thing is multiple analysis. You hear this all the time in the diet claims. Several studies have shown the weight gain. Well, that means they did multiple studies. And that means if they did lots of studies and some of them didn't work, and they did some studies and some of them did work, you should be really, really nervous. Because remember that our alpha level is also the chance of a type 1 error. And remember, a type 1 error was rejecting the null hypothesis when in fact the null hypothesis was true. Well, if you did that, remember, 0.05 is 1 in 20. So if we tested some diet pill and we did 20 different studies, and in one time we got statistically significant evidence, that's what we would crow about in our advertising. But it's probably a type 1 error, because you would get a type 1 error 1 out of 20 times. And this is also really the danger in modern publishing and scientific research, is that people don't publish their failures. People only publish when they get statistical significance. And so we don't hear about the failures. And so it's possible that there have been 20 tests and only one of them got published, the one that had the positive results, and it could be a type 1 error, which is why in true research, if you get a result. So the first thing you should do is have somebody do the same experiment again to see if they get the same results. Let me show you what we're talking about. Suppose that there were 20 significance tests that were conducted. In each case, the null hypothesis was true. What is the probability we avoid a type 1 error in all 20 tests? Well, let's think about that. The chance of having a type 1 error is 0.05. So the chance of not having a type 1 error is 0.95. And so the probability of not having a type 1 error in all 20 tests is 0.95 to the 20th power. So there's a 0.36 chance that we never make a type 1 error, which means there's a 64% chance that we will make at least one type 1 error in those 20 tests. And so finding one significant result in 20 is not a surprise. As a matter of fact, it's more likely than not. So that's basically it. And we're going to be doing a lot of more hands-on stuff in class. This is just the end of the theory here for this unit. Significant test for the mean of mu of a norm. This is just a review of how we do the t-test, the t-statistic. Remember, degrees of freedom is n minus 1. You always need to check the conditions for any test for mu that you do, random, normal, and independence. Remember, normal, if n is less than 30, you're going to have to show a graph or know that the population distribution of the original population isn't approximately normal. We're talking about confidence intervals and their link to two-sided. We talked about that in class. We talked about paired data. And then we talked about using tests wisely. And these generally don't come up on FRQ questions, but they will come up on multiple choice questions. So we have to understand the limitations of the tests. We'll see you next class, and then the next video will be the review video, and your test will be on Tuesday.